I just ask him to turn on the mic, and it's easier than getting out of bed. Okay, let's start. Turn it off. This one? Okay. That was easy. I don't think it'll be that easy to turn that construction node on. Okay, so we'll pick up from last time. We started talking about parameter estimation and specifically about Bayesian parameter estimation. So the setting is basically the standard Bayesian decision-making setting where there's some unknown here, some observation here, and some action here. So the unknown in our case is, since we're Bayesian, the unknown state of the world is a random variable, which is the parameter. So unknown parameter, which, since we're in the Bayesian setting, it's a random variable, so I will, just to make that clear, I'll denote it by uppercase theta. Okay, so it's a random variable, and we treat it as such. Then there's the observation, x, which is, in any case, a random variable, and that's generated by p of x given theta. Okay, so there's some value of theta that's chosen according to a prior. That's this lowercase theta, and then x is generated according to this distribution. And then we take the action, which is the estimation, which is the function theta hat of x. Okay, so x is a random variable, and theta hat of x is a function of that random variable. Okay? And that's our estimation, and clearly we'd like this estimator to be close or to somehow be a good estimate of this unknown parameter. Okay? And when we're in the Bayesian setting, all we need to specify in order to complete the specification of the problem is the prior on the parameter and the loss function. Okay? And we, in previous class and in Roy's exercise and your home exercise, we play with different definitions of those and see how you get different outcomes. Okay? So, so some examples we've seen. Okay, so actually before the examples, so the key thing that you get out of the Bayesian setting is what we call the posterior, which is, so let's say theta is continuous, and let's say there's a prior here we call f theta. You know what, let's make x continuous as well, so everything is densities, okay? So note, you know, that theta can be a continuous parameter, and x can be either discrete or continuous, okay? So they don't have to live in the same domains at all. Okay, so anyway, if you're Bayesian, the key thing is that it allows you to talk about this following nice thing, which is the posterior of the parameter given the observation. Okay? So it reflects your uncertainty about the parameter given what you have observed. All right? Okay. And then once you have that posterior, I mean, you eventually want to just provide a single estimate. The posterior is the whole density, right? You want to provide a single estimate. Okay? So what can you do? If you want to turn this into a single parameter estimate, so there are sort of two natural things you can do with the density if you want to provide a single number. One is to take its expectation, right? To take the expected value of theta under this. And the other is to take the theta that maximizes this, okay? So, so let's say this naturally leads to two estimators. One is what we call the theta hat L2 of x, which was the expectation of theta when taken according to the posterior, I'm sorry, f. Okay, or in other words, it's the integral of f theta given x, theta. Okay, so it's the expectation of this posterior, and the other we defined for you in class, we call theta hat map of x, which is just the arg max over theta of phi of theta. Okay? So generally, these two things are different, right? If I give you a density, let's say this is theta, and this is f of theta given x. Okay, let's make this more clear. Okay, what is the map here? If this is the posterior, theta hat map. Map stands for what? Maximum posterior. Okay, so it's whatever maximizes the posterior. So this guy is theta hat map in this case of x. And what is the theta hat L2 approximately? It'd be, I mean, we need to take the expected value, right? So there's some mass here, some mass here. So the expected value is probably somewhere here. Okay. Okay. So generally, it's two different things. Okay. For Gaussian, everything's the same. Why?
Because the expected is the highest flow.
Right. Okay. Okay. But generally, they're different. Okay. So we can play many more games with this Bayesian setting by changing the loss function, by changing priors, etc. But we're close to being done with it because I want to present a different perspective. So I just want to focus. Oh, this is F. Sorry. I just want to focus for a second on the map estimate and ask, when does the prior matter? Okay, so we've seen when we talked about multiple or IID observations, we claimed and we sort of showed that when you have many observations, what happens? As you get more and more observations in the Bayesian setting, the prior matters less, right? And I think Roy argued for this more in his class. So let me just talk about that. So map with IID observation. I thought we took care of that. Ooh. Really wants to vibrate this thing. Okay, so assume xn is IID from, let's say, f of x given theta. Okay. So here, instead of a single observation, you have n observations. Okay. Then let's look at the posterior. So f of theta given xn is well, it's equal to f of xn given theta times f of theta over f of xn. Okay. Right. And then we usually like taking the log here. So log of f theta given xn is log of f xn given theta plus log of f theta minus log of f xn. Okay? So this is the usual thing. So you see again these two powers here, right? So there are two things involving theta. One is this thing, which says how likely is xn given theta. So this has to do with the observation, and this has to do with the prior. Okay? And each pulls in a possibly different direction. And then it's clear that theta hat map of xn, which is the argmax of this thing, this additive term here doesn't matter, right? Why doesn't it matter? Doesn't depend on theta, exactly. So it's the argmax over theta of just these two things. Okay. And now, because of IID, what is this thing? It's f would be a product of the individual observations. So this would be sum over I log of f xi given theta plus log of f theta. Okay? So as you get more and more observations, what happens? What happens? So this is I equals 1 to n, right? So as you get more and more observations, this thing is still, it remains the same, right? And here, the sum keeps growing, right? Okay? So it's clear, and we have sort of shown it formally, but it should be clear that as you get more observations, this thing will grow and will overcome the prior, okay? So eventually, as n goes to infinity, this will scale in the same way. It will scale with n, and then the prior will just not matter. It will not affect the maximum. Okay? Does that make sense? All right? Because whatever this thing here is a random variable, right? And what you do is you take a sum of n such random variables. Okay? So if you think of the expected value of this thing, what is it? It's n times the expected value of this random variable. Right? Yep.
So when you have only one observation, they have the same power in the equation.
Right.
And then it will be exactly in the middle between the set of your observation and the set of...
Well, it will be the maximum of these two functions. So you're adding two functions, okay? So it's not in the middle per se. It's just you take these two functions, you add them together, and you take the maximum, okay? So it's not only, we have to be more precise here. It's not only about how many observations you have. It's also about who feels more strongly about what theta should be, okay, in quotes. So, for example, the prior could be very opinionated, let's say, okay? You could have a prior that is, let's say this is theta and this is f of theta, and the prior could be very peaked at some value, okay? So when you take the log, this will be, say, minus infinite, and this would be large, okay? And then it would be hard for the likelihood to compete with that, okay? So it's a competition. Anyway, for any n, it's a competition, okay? And the answer is just the outcome of the competition, essentially. Yep.
From this equation, it's clear that the term, the additive log size gets very big when n grows to infinity.
Right.
But what we're looking for is the argmax over theta. So I don't exactly understand why the fact that this term grows very large makes it stronger in affecting the argmax of theta.
Because, okay, you could build cases where you have to take a very large value of n for this to dominate. But if you think about this function, okay, so think about the function here and the function here, okay? The scale of this function is much larger than the scale of this function, okay? So let's say the contribution of this to the sum is minimum, okay? So if this function, let's say, is like this, okay? And this function here is like this, okay? So it wants to be maximized here, okay? But since this function has a scale that's much larger, this will not affect the maximum, okay? And this will just the effect will just increase as you increase the n. Okay, we'll show this a bit more formally later, but I just wanted to, I mean, first of all, I want you to just accept the fact that the prior gets washed away as you have more observations, okay? You'll see it in different formal ways in exercises. Okay, and that's basically the reason. Okay, so now this gives us a nice jumping, yep.
Do we have some function about how our prior is supposed to look like? Is it supposed to be similar to x given theta?
Right, very good question.
If you have only one value, like, I don't know how you call it,
Like deterministic?
that has
Delta function. Yep.
exactly. So
Yes.
then it will always be the dominant part.
Right, exactly. That's what I drew here. Okay. So there is no rule for stating the prior. Okay, this is sort of the religious aspect of the Bayesian setting. That you determine a prior based on either prior knowledge. Okay, so for example, if you're looking at distribution over weights, then you would require the mean to be non-negative, say. Okay, because it makes sense, right? So you could inject sort of prior knowledge of that sort to your prior. Okay, you say, okay, the f of theta should not have a density where I know the parameter cannot exist. Okay, so that's one thing. And another is computational convenience. Okay, so for example, we choose last time I did an example with the Gaussian prior because I mean it's computationally easy. It's not unreasonable as sort of describing the range of parameters that or values that the parameter can come from. Okay, but specifically, if you ask about the delta function, if you set the prior to be a delta function, it's as if you're saying, I know what the true value is. Okay, if it's very peaked on some value of theta, say 3, okay, it means that you have very strong belief that it should be 3. Okay, if it's infinitely peaked there, you don't need to do all of this because you know. Your belief is so strong that you know. Okay, you don't need any evidence. This is really like religion in a sense, right?
That's the difference between believing and knowing.
Right, but this allows you. The nice thing is that the prior allows you sort of a midpoint between believing and knowing, right? You don't have to commit. You say, okay, I think it's somewhere in here. I don't know for certain what its value is, and I'm allowing through this mechanism, okay, or generally the mechanism of the posterior, to balance between my prior belief and what the observations tell me. Okay?
So we're supposed to state like how much do we believe in our prior, and that's how we.
No, the prior itself expresses your belief in whatever theta is.
To justify it in some manner if we're supposed to, I don't know, an exercise or just to give you our prior.
So there are cases where you can get even empirical estimates of the prior. It's sometimes called empirical base. So let's say you give an example. Okay, we talked about the height distribution in different countries last time, right? So maybe you've seen like 50 countries, okay? And you have a rough estimate that the mean height in countries generally is between 150 and 170 centimeters, okay? So you would construct a prior that has some or the majority of its mass in this area, okay? While allowing maybe some tails for other values, okay? So it makes, I mean, there are many settings where you can construct a prior based on empirical observations, okay? But generally, there's no correct way of doing it, okay? In the Bayesian setting, it's a prior assumption, okay? All right, so as before, as in when we talked about decision, Bayesian decision, the nice thing about the Bayesian setting is that you specify two things, the prior and the loss, and you're done, okay? It tells you exactly how to behave, and it's optimal in the sense of minimizing your overall loss. Okay, but obviously there are limitations or objections. One is that you need to specify a prior, and this is to some degree an issue of belief. And your performance measure is the expected loss over this prior. Okay, so the thing that you want to optimize is the loss that you would incur if you repeatedly play the game of someone drawing a parameter from the prior, you observing x, you specifying the estimator, and suffering a loss. Okay, so the thing that you optimize, the loss that you optimize, is closely related to the prior. Okay, so if you're not sure about the prior, if the prior doesn't reflect what really happens in the world, then it's not clear that this is the optimal thing to do. Okay, so now we're switching to a non-Bayesian setting, which means we don't accept the notion of a prior. Okay, so this is all gone. Let me erase whatever is illegal in the non-Bayesian world. Okay. So in the non-Bayesian world, you're not allowed, okay, definitely no non-prior, okay? And this thing, can I write it this way? Capital theta? What does that mean? That it's a random variable, okay? So it is no longer a random variable. There is in the world, there is in your world a number, theta, that specifies the distribution from which you see the observations, but it's not a random variable. In your world, there is a value of that theta, for each person or in different settings, there might be a different value for this parameter, but we don't know anything about this parameter as a random variable. Okay? It might have been just specified once in the beginning of the universe, like the, I don't know, the mass of the electron. Okay? So there are no, I mean, you might not accept the fact that there are random universes, each with a different mass for the electron, etc. There is this number. You don't know it, but it's there. Okay? And you don't want to think about priors, etc. Okay. So we will no longer be allowed to write things like that, like posteriors. Okay? Because you're allowed to write posteriors if this thing is a random variable. We will keep this notation of f of x given theta. Okay? Because we're conditioning on theta, okay? So it's true that when you write this, you think of theta as a random variable, but we'll just keep this notation and agree that we're not thinking of x that way, okay? So if you look at the non-Bayesian literature, this will usually be written as f of theta, subscript theta, x, or f of x, what do you call this thing? Semicolon, theta, okay? So to highlight the fact that theta is just an index and not a random variable per se, but we will keep this notation just not to introduce more clutter. Yes, Thomas?
Is this a function we have to know in this case?
Yeah, this is the parametric family, right?
It has to be exponential, Gaussian, or something we can use if we only know one parameter.
Right, it's the same. That part stays the same as before. So there is a parameter theta. There's a range of values of theta, and each value of theta specifies a distribution, okay? Right? Yeah. So that is still the same. We still have a parametric family of distributions, and we're interested in theta. Okay, so if we look at this thing, what is the only thing that we're allowed to keep from this? This here, okay? Why? Because this is conditioned on theta, all right? You don't need theta to be a random variable to talk about this thing. What is this thing? It says, I don't know what theta is, but for each different value of theta, there is the likelihood of my observations given that theta. Okay? But you don't need to think of theta as a random variable for this. So that's a good thing. The other good thing is, as we've talked about before, if you have a lot of data, this is actually the dominant term. Okay? So even if you're Bayesian, you accept that this thing has some has to have some importance, right? Because if you're Bayesian and there's a lot of data, still the thing that you will maximize is this thing, and you will forget about the prior, right?
You're talking about the IID case, but in general.
Right. In general, if you're Bayesian, obviously there's, as I said, there's always a competition between these things. Okay, but I'm trying to find a sort of a thread for the non-Bayesian estimator to start from. Okay. And so we're saying, okay, this seems like a reasonable thing to want to maximize. Okay? Right. So, non. Right? So, okay. Right. So, indeed, the most popular or often used estimator in the non-Bayesian setting is just to maximize this thing, okay? And it has a name. What's it called? Maximum active. Did we mention? I think he got close to mentioning it. Maybe not. The maximum likelihood estimator is defined as follows. It will be denoted by theta hat ml of x, and it will be just the argmax over theta of f. Well, this is x given theta. This is for continuous, or for if you have a discrete x, discrete x be argmax of theta p of x given theta. Okay? So, okay. And this thing here is called the likelihood function. Okay?
Only the f of x n given theta?
F of x given theta. That's the likelihood. Okay?
Why?
Because it's the likelihood of, it tells you how likely x is to be observed given a particular value of theta. Okay?
Every probability tells you how likely
Right,
it's
yeah.
to happen.
Right. It's
So
just
why
the name.
is it-
Why is it called?
But is it, does it have certain importance or?
Well, it's the thing because it's the thing that you in maximum likelihood. It's the function that you maximize. Okay. They didn't want to call it maximum. Well, I guess it's historical. You could have called it other things. Okay. Maximum likelihood is the name of the estimator, and it's not because you're maximizing this thing, which in this context is called the likelihood. Okay. Let me just state that it's often more convenient to maximize the log of the likelihood. Was this true? Yeah. Okay. So log is a monotone function, so you can maximize
You
that.
do every time.
Right. Yeah. Right. We did it there as well. Okay. So this is called the maximum likelihood estimator. I think probably Fisher was the first to introduce it formally in the early 20th century. Okay. So you should be careful when how to interpret this. We're not maximizing the probability of theta. Okay. Since we're non-Bayesians, we're not even allowed to say that. Okay. So we're not maximizing the likelihood of theta given x or anything like that. Okay. This function is a function of theta. Okay. And for each value of for fixed x. Okay. So in this context, x is fixed. And we're varying theta, and for each theta, you ask theta, how likely are you to generate this x? Okay? You write that in that number, and this is the function that you're maximizing. Okay? So this function looks like this. There's a theta, and there's a f of x given theta for a specific x. Okay? So this whole thing happens for a particular observation, and there's a function here. Okay? And maximum likelihood is just the maximizer of this. All right? Good.
There's going to be just a simple summation due to the log properties.
If you're IID, okay, then it's just this thing. We did it here. Right?
But we're talking only about IIDs now, aren't we?
Yeah. So when I said f of x, x can be multiple observations and can be a single observation. If x is xn, so it's multiple observations, this would be a summation. Okay.
So you just go for every observation, you check how probable it is.
No, because you need to maximize. I'll do an example and you'll see. Okay. Okay. So just so you know, this is the most popular parameter estimation method. And if you have a parameter estimation problem, this is the most natural thing to try. It's not optimal. I mean, we'll talk about in which senses is it good or bad, but it's not. It's certainly not the best in any sense. It has some desirable properties, but you can't say that it's better than other things. So in other words, there are other estimation methods which you might want to consider. Okay. And we'll talk about the notion of optimality for these things later. Okay, so let me do an example. Let's say a Gaussian. Let's say we have a Gaussian distribution with unknown mean theta. Okay? So this is your parametric family. So f of x given theta is a Gaussian with Gaussian on which variable? Sorry? X. Okay? Right? With mean theta and say variance 1. Okay? So from now on, all distributions, okay, distributions will only be over x. So it's less confusing than the Bayesian case, in the sense that there's only one thing that things can be distributed over. All right? Okay? And then let's assume IID, assume IID sample. Denoted by XN. Okay? And now we're asking what is the maximum likelihood estimator for this theta. So we need to write the likelihood function. So log of fxn given theta is, let's remind ourselves what is okay, let's write it here. This is 1 over square root 2 pi e minus half x minus theta squared, right? Okay, this is just a Gaussian. So if I take the okay, let's write it explicitly. So it's log of the log over the sum of fxi given theta, right? Oh, sorry, sum of the log. Yeah, sorry. Right, good. So this is sum over I log okay, this way minus log square root of 2 pi minus half xi minus theta squared. Right? So I just took the log of this. Good. And now what do I want? So this is the function. I'm not going to write it further at this point. What do I want? I want to maximize it, right? So in some cases, it's just technically, you want to sort of take the derivative at the right point, okay? So there's no point developing this further because I can take the derivative here and it'll be simpler. Okay, so I could have opened the squares and all that, but no point. Okay, so we want the maximum. So take derivative with respect to what? Theta, right? So x's are fixed here. Okay, they've been fixed. We saw this observation, and that's it. Okay, so d log, so actually d log f to d theta is, so what happens to these guys? They vanish, right, because it's a constant. And here I have, so minus half, the derivative inside would also be minus, so that the minus goes away. So it's half sum over I xi minus theta. And this should be, sorry? Ah, yes, right, that's twice. That's right. Doesn't really matter. And I want to set this to 0, right? So I'm interested in the maximum. Okay, so this goes away. And what do I conclude from this? So this is sum over I xi equals n times theta, right? Because theta is added n times. And from this we conclude that theta hat ml, which is the maximizer of this thing, is 1 over n sum over I xi. Let me just say in brackets that we need to convince ourselves that what? Right, that it's a maximum. Okay, so we took the derivative and set it to 0, but that's just a necessary condition for being a maximum. We still need to show it. So I won't show it because it's actually why is it true that it has to be a maximum in this case? Sorry? Well, why? Or it could be a stationary point as well, right? It could have been that. Well, it's a log of that, yeah. But it could have been. What could have been the bad case for us if this looked maybe something like this, okay? Where we took the derivative and we found this point, which is the only place where the derivative vanishes, okay? but the maximum is actually at infinity, right? Possible, all right?
It is actually
But
possible though, because we know that the minimum here is 0, don't we?
the minimum. Well, you know that the minimum.
The minimum is 0 because it's a probability function.
If you take, you're saying that if you take theta to infinity, this would go to 0. That's true. Okay, so you could argue in the different ways why. Obviously, it is the maximum. Okay, you could argue in different ways. One way is just to look at this thing as a function of theta. What is this thing? It's a quadratic, right? It's a quadratic function with a minus, so it's just an inverse parabola, and therefore it has a single maximum where the derivative vanishes. Yep.
Is it legal if we have like something in the homework or to argue for it without?
So you need to, I mean, so this is a formal, if you say, okay, this is it's a second order function, okay, or a parabola, and a parabola has a maximum where the derivative vanishes, that's fine, okay? There could be cases where the function is different, and you might need to argue something else, like looking at the second derivative, etc. All right. So another nice thing about maximum likelihood estimators is that they're usually very intuitive, and they sort of make sense. If you had to guess something before, it's very likely this is what you guess, right? So if I told you you have n independent observations from a Gaussian, you want to know its mean, what would you say? Take the average, right? Okay, so that's a good thing. You remember we had in the Bayesian case. What did we have here when we used the prior on the parameter with 0 mean and unit variance? We had 1 over n plus 1 here, right? Which reflected our prior belief. Okay, so and that might have been a bit less intuitive. So this is could argue makes sense. Okay, let me just state without showing this, we will show this in the exercise. I have this. Right, so let's say our example, let's take a more complicated example now with Gaussian with unknown mean and variance. Okay, so now both are unknown. So f of x given theta will now be Gaussian with mean theta 1 and variance theta 2. Okay? Yep.
Just one question about the method. So if for a big N we're supposed to have the same result for this method as we will have for the Bayesian method.
That's right.
So the reasonable thing to do is immediately to do this because it's much easier, right? And the prior is negligible anyway, so.
Well, it's as I said, it is a very often used estimate, so people do use it.
That's the reasonable thing to use if you have a big N.
If you have large N, well, it won't really matter, right? You can use whatever prior you want, and it'll be washed away, right? So it'll end up.
Stupid to use prior if you're going to wash it away.
I think if your observations, if you have many observations, okay, or that you think whatever prior I would have had, it would have not really mattered, then you would anyway arrive at the same estimator, and yeah. But the Bayesian setting does make sense in many cases, and you never have an infinite number of observations. Okay, you always have a finite number of observations. Okay. Actually, in a sense, the Bayesian setting prevents you from giving silly answers. Okay, because it prevents you from, if you know that the parameter cannot reside in particular values. Okay, it takes you away from that. Like I said last time, with the height distribution, if your first subject is, I don't know, 6 foot, okay, or 2 meters, the maximum likelihood will tell you what is your estimate of the mean. It's 2 meters, right? But the Bayesian setting might tell you, okay, 2 is actually not very likely, so you have to push it to the left a bit. Okay.
But it will work only
Well, the effect of the prior will diminish as you get more observations, which makes perfect sense, right? Okay. And many things in life are actually we have very few observations. This is something that people are very good at for making inferences based on very little data. Okay. So, and there's a lot of actually psychophysical evidence and cognitive evidence for people using Bayesian strategies in inference. Okay. Which makes sense. We know intuitively that we use a lot of prior information when we make decisions. Okay. All right. So what's the answer here? So to do it, what do you need to do? You need to take, now it'll be partial. So now the likelihood is a function of two parameters, right? So theta here includes the two. So you need to do d log f of x given theta 1, theta 2 to d theta 1. That will need to equal 0. Well, it's xn, we said. And derivative with respect to the second parameter is also 0. Okay? So you have now two equations in two unknowns, and you need to solve this for theta 1 and theta 2. Okay? All right? Okay. So generally, this might be nasty to do. This might not even be a closed form expression. In this case, it is tractable, and the answer is, okay, that theta 1 hat, I'll drop the ML subscript, is the same as before. Sort of makes sense. Okay. Okay. So function of x. These are the maximum likelihood.
The mean and the variance that I wanted to
Yeah. Okay. You have a Gaussian, you don't know its mean and variance. You observe a sample, you want to say what are the mean and variance.
You take a derivative with respect to the mean and with respect to the variance.
With respect to the parameter. Yeah, it's the same as there, right? You have two unknown parameters. Don't think of them as mean and variance. They're just two unknown parameters that specify the distribution somehow, okay? And you do the same. It's just you want the maximum of the function with respect to two variables, okay? So now the likelihood function looks like this. There's theta 1 and theta 2, and there's no way I can draw this. Something like this, okay? Two-dimensional function. Right, okay, good. So what is the theta, what is the estimator for the variance? It is, yeah. So I said, let me write it. It's ML1. Do you want 1 ml or ML1? 1 ml, yeah. All right. 2 ml. So sum over x I. So what's the variance usually? It's the deviation from the mean, right? So you take the sample. You want the deviation from the mean, but you don't know the mean. So what would you put instead of the mean? Your estimate of the mean, right? The average. So which is just this theta 1 ml xn squared. Okay? So it makes a lot of sense. You're estimating the variance. The variance is the squared deviation from the mean. You're looking at these samples. You don't know the mean, so you're taking the deviation with respect to the mean that you estimated, okay? And then squared. See, again, very natural. Makes a lot of sense. Good. All right. So that's one example, and you'll do many more in the exercise. Okay. So up to now, we just proposed this estimation scheme. We don't know whether it's good or bad. Okay. We need to have some. I mean, it'd be nice to be able to say something about this thing. Okay. So in which sense could this be good or bad? Let's just bring up a couple of options, and then we'll do them after class. So recall, you have a parameter here, theta. There's no prior or anything like that. Generates an observation. You generate your estimate. Okay?
So here we can go from the squared difference or the difference between theta and theta.
Okay, but the issue is that you don't know what this thing is, right? Okay? So let me give an example just for you to think about. Let's consider, let's say, the first example, example 1, and the estimator theta hat of xn, let's give it a name, theta hat silly equals 3. Okay? So here's an estimator. It always gives the value 3. Is it good or bad? Right. When will it be very good? When the real value is 3. Okay? Otherwise, not so great. Okay? When the real value is 3.1, still okay if you measure squared error. When the real value is 10, pretty horrible. Right? Okay. But it shows you, even this thing, okay, that when we talk about the quality or the optimality of an estimator, it's going to get more complicated now. Because a given estimator might behave nicely for particular values of theta and not so nicely for others. Okay? So there is, whatever you measure of the optimality in this theta axis, let's say this is the quality of theta hat, your estimator, is going to be a function, right? So for example, in this case, it'll be a function, well, let's call it loss. So low is good. So in this case, when theta equals 3, your loss will be 0, right? And otherwise, it'll be something else, all right? Okay? So you can think of this thing as the performance function, okay, of your estimator. Right? So for any estimator, I could play the mental game of thinking, okay, had the value of theta been something, how well would the estimator do? Okay? All right? So for any estimator you give me, I can draw this function, right? I can simulate and I can draw this function. How will I do it? I will go over different values of theta, draw samples x, and measure the expected performance of your estimator, and then I provide you, this result sheet with this function, and this is the quality of your estimator. Okay? All right? And that's basically it. I mean, we can't say much more than that in terms of evaluating an estimator. So now let's say you have another estimator, theta hat really silly, which is always gives 5. Okay? So what would it look like? It's here, right? So it will look like this. So which one is better? Well, yeah, you can't really say. But here's another one that looks like this. I don't know. Let's say it looks like this. So which one is better? It's hard to say. I mean, there's to each its own, right? And it depends. What does it really depend on? Which values of theta are you really going to experience in life? And this is where the Bayesian thing comes in, right? If you know which ones you're looking at, then you might as well be Bayesian. And you can avoid all this embarrassing need to decide between 3 functions where neither dominates. Okay? All right. So that's something to think about. And next class we'll give different performance measures. Question? Okay. אז היא בדיוק עושה את האינטגרל על זה. כן. של היום, או זה שקיבלתם אתמול? שפורסם אתמול. אוקיי. בטח, אוקיי, כן.
זה האוברול בזה.
בטא, ואז תהפוך לשיפוט ל-X פונקציה כזאת.
לא, אבל אתה יכול גם הפוך, אתה יכול... לא, אבל יכול לעשות אינטגרל על תטא, של תטא, נכון? כפול המותנה על תטא. אם...
לא צריך לחקור,
מה? אוקיי, אז אם של בטא, יש לך, וזה בטא, ופה יש לך איזה תטא אחר, נכון? ג'י תטא, זה גם בטא. ג'י תטא, אוקיי? אז יש לך פה מכפלה של שתי תטא.
פה
זה גם בטא.
כן, אז לא דיברנו על זה שלדעתי תכף נעשה את זה.
כן, זה תטא...
התטא היא לא...
אני כאילו שומע, אתה יודע, דברים שנאמרו פה ונאמרו פה וכאלה.
לא, יכול להיות שיש פה עד כדי קבוע נרמול.
קשה לי עוד לראות את זה.
ואז אם אתה יודע שזה בטא, וצריך לקבוע נרמול החוצה, אתה יכול להשתמש בזה. לרוב בשאלות האלה לא צריך לעשות אינטגרלים, אני צריך להשתמש באינטגרלים ידועים, או של נרמול. אבל כשאני אומר שזה משהו שקיפות,
לא, רק ששם דיברנו על מטריצות.
אז בעצם צריך בספרטי את האינטגרל, נכון? אם אני אומר לך, גאוסיאן הוא...
דיברתי שם גזרנו על
האינטגרל שלו על פני X הוא... לא קיבלת אינטגרל במתנה. מעצבן, קיבלת עוד אינטגרל. אז לא אומר בשאלות האלה, זה צריך להשתמש במתנות האלה, אוקיי?
כן.
אני בא לנו רואה שזה באמת זה שלנו. בסדר?
אני רוצה לשאול את זה ממש בקצרה.
כי בבוקר היא קטע טלי אמרה לי שזה מנצלת בגלל שהם שופטים כל כך הרבה, יורדת בהם שופטים כל הזמן. לא יודעים להוציא אותם, ואז הם משחקים את זה.
אחד מנצלת כפונקציה של אלפא.
וגם תוכלי לא מגיעה כל הזמן.
צריך לקחת 3 אנשים
שיש לה יותר מדי אוכל במשחק, אז זה יותר פתאום לחץ. נראה לי שזה יקרה לה הרבה.
זה ככה, אני חושב להתפלגל את הפונקציה האלה.
זה לא אלפא.
זה לא אלפא. עכשיו אני צריך...
אתה צריך את אלפא כפונקציה של T ובטא כפונקציה של T.
אני לא באמת חייב לדעת.
לא, זה יכול להיות.
אני צריך את אחד מנוצח.
אוקיי.
יש לי 3 מקרים, נכון? יש לי מקרה אחד שבו תטא 1 ובטא 2.
זה הפרמטר? זה דרך כלל בסדר 2? אז... בטח להניח
אני לא מכיר סתם
זה משנה בגלל שאלפא בין נגיד שזה נקודת האינטי שזה 1
אם זה ממש מטריד אותך, אז אפשר לראות
עיקרון מאוד עקרוני.
השאלה שלי על מצב הזה, כאילו מה שכאילו שאלתי ותלמיד גדולה יותר, בגלל שמוגדר שם החלטה של נציג.
נכון, זה הופך את המשמעות של ההחלטה
בהחלטה. ואז השאלה, במקרה שתטא 1 ותטא 2 שוות,
אם שוות
אז
אתה לא יכול...
פי גדול מאחד, ואז ראינו בכיתה, לא ראינו למה, אבל ראינו שאלפא שווה 1 מינוס בטא, נכון? זה הרוב
לא, אם הם שוות, כן, זה אמור להיות על האחסון, כי אתה בעצם לא יכול, אין לך שום אינפורמציה.
כן, אבל יש פה איזשהו פרדוקס. בגלל שלפי כלל ההחלטה, זה לא משהו שיכול להיות לערכים רציפים לאורך כל הקו, אלא בתכל'ס זה יכול לקבל רק את הערך הזה או את הערך הזה. כאילו יש כאן איזה בעיה בהגדרה. עכשיו, בגלל שה-T הוא גם ככה רידנדנט,
כן, שאם הם יושבים על אותה נקודה, אז...
כאילו במקרה גבול, אז כל זה הגבול.
לא, אבל זה לא נכון. כי נגיד שהם אותו פילוג, אוקיי?
כן.
ועכשיו אתה שם את הסף פה.
כן.
בסדר? אז מה זה שתי הטעויות?
אבל אתה לא יכול לשים את הסף פה לפי ההגדרה הזאת. לא, כי יתקבל לך T גדול מאחד.
בלייטיות הבנתי.
נכון, בזה אתה צודק. אם אני מדלג על זה, וגם ככה...
אז השאלה מה אתה עושה את המבחן סף? אם הוא על נכון,
גם ככה אני לא צריך את זה בסוף, באף אחד מהמקרים. אבל לפי ההגדרה הזאת יש לנו בעיה.
נכון, אם זה תעשה את זה כמבחן סף על הלייטיות, אז באמת אתה לא יכול לקבל כל הנקודות האלה.
או שאני רוצה להגיד שלפי המיון הזה, ראינו שכל זה מקרה שיושב על הגבול, ולכן זה יהיה לגמרי רנדומלי, ואלפא תהיה שווה 1 מינוס בטא.
לא, אבל זה נכון שבאמת, זה מבחן, אני לא יודע אם לדעת את זה, אני חושב שרועי היה אמור לעשות את זה, משהו
כאילו שאתה לא יכול לקבל את כל ערכי אלפא ובטא. למשל כש-X הוא דיסקרטי, אוקיי? במקרים, נגיד שיש לך פה שתי קוביות ארנולית, להחליט שתי מטבעות. ואתה עושה מבחן סף נראות, אז יש רק איזה 2-3 סופים שהם בכלל רלוונטיים, נכון?
כן, אבל פה הוא לא דיסקרטי.
נכון, אבל המקרה שהם שווים, זה כאילו באמת...
מקרה גבול פשוט.
כן, שאתה לא יכול לקבל את כל הסופי הבטא.
כאילו אני צריך להגיד שככה זה נראה כפונקציה ש1 מינוס בטא כפונקציה של אלפא, פשוט זה 1 מינוס בטא שווה אלפא.
היא אומר כמעט, זה שאומרים P2 במיתי נגיד, זה נוכל ואם שווים, אז זה 1, ואז השאלה אם...
יוצא לי T שהוא לא פונקציה של X.
לא, אתה משחק כאילו עם T, ואז T עד 1 זה משהו אחד, ומ-1 משהו אחר.
כן, אבל זה גם ארביטררי, כאילו...
לא, זה תלוי בפריים.
מה זה עד 1? 1 זה אומר היחס בין שתי הפונקציות.
היחס בין הפונקציות
הוא תמיד 1.
נכון, זה יוצא לך ככה. אז זה אומר שאם אתה...
זה אומר שרק כשאני גדול, כאילו... אי אפשר להבין את זה, זה משהו פילוסופי.
לא, אבל אתה גם לא תראה את ה-X.
רק במקום שבו היחס בין שתי הפונקציות גדול מאחד, אז זה לא קורה אף פעם.
כן.
אבל רק במקום שזה קטן מאחד, אז זה לא קורה אף פעם. ואז אנחנו מתחילים להיכנס לאם זה גדול שווה,
מקרה גבול כזה מציג כאן...
זה פשוט בעייתי עם ההגדרה של ה-T.
לא, ההגדרה היא בסדר, אני אומר שהמבחן הזה אולי הוא...
ההגדרה היא בסדר, פשוט לא מתאימה למקרה הגבול. נכון? כאילו, היא לא אומרת לך מה לעשות במקרה הגבול.
לא, אני אגיד לך, כן, כפונקציה של T, אם T הוא, נגיד אתה אומר, אני אחליט 1 מ-X זה, נכון? זה מבחן קצת, כמו שהוגדר בזה. אז עכשיו, אתה אומר, במקרה שהם שווים, באמת זה, זאת אומרת, אני אחליט 1 עם 1 גדול שזה מיסוי, אוקיי? זאת אומרת, עכשיו, שאלה מה T? אם T קטן מ-1, אוקיי? אז אני תמיד אחליט 1. ואז תהיה לי שגיאה אחת מיסוי 0 ושגיאה אחת 1, נכון? אם T גדול מ-1, אז זה הפוך, אוקיי? זהו, אז זה באמת, זה כמו שאמרת, זה 2 נקודות. זה בדיוק 2 נקודות האלה. וזהו, זה לא קר, זה שתי...
כאילו זה תלוי באיך אני קובע מה יותר אכפת לי בעצם בסופו של דבר, מה אני רוצה לבחר, איזה סוג של...
זה הבחירה של T, תגיד, האם אתה תמיד תחזיר 1 או אתה תמיד תחזיר 2?
לא, נגיד אם T היה שווה 2, זה היה אומר שאנחנו צריכים שהפונקציה הזאת תהיה ממש יותר גדולה.
אבל היא לא יכולה להיות, כי הפונקציה הזאת היא...
לא, אם הם לא, אז במקרה שהם לא שווה.
ברור, נכון, זה כל הרעיון של הרוב, שהוא אומר, תסתכל על היחס הזה, ועד כמה היחס הזה צריך להיות משמעותי, זה מה ש-T קובע.
אז נגיד יכלתי להגדיר את T חצי, ואז היה אומר לי תמיד לבחור את זה. אבל אז כאילו התשובה פה שזה תלוי בהגדרת T.
אבל כל הרוקר תלוי בהגדרת T. נכון, מה זה הרוקר? זה ללכת ולשנות את T, ולכל ערך של T אתה מקבל צמד אלפא.
לא באמת, בגלל שבכל המקרים האחרים יכולנו להתעלם מהדברים שמצאנו ל-T.
כי היה לך דרך לעקוף את זה, אבל בהגדרה זה ההגדרה. נכון, במקרים הרציפים אתה יכול כאילו לעשות את זה.
זה מקרה לא פשוט בכלל, שחושבים עליו לעומק.
לא, אבל הנה, דיברנו על זה והגענו על זה שתי נקודות. יש הגדרות אחרות להגיד. אוקיי.
טוב, מה זה 2 נקודות? אם T שווה חצי, זה לא חייב.
לא, זה 2 נקודות.
נכון, כי anyway,
זה 2 נקודות שמתאימות לזה שאתה תמיד מחליט 1 או שאתה תמיד מחליט 2.
זה ייפול כאילו או משמאל קו ההחלטה או מימין קו ההחלטה וזהו. בסדר, תודה.
שאר דלתה בהינתן לא מזרחים, דלתה בהינתן זה קטן שווה. העניין הוא שאתה מוכיח שמשהו אחד גדול שווה והשני קטן שווה, אז אתה בעצם דרך היחידה של המסתדר זה שזה שווה. ואז בעצם תנאי באלף הוא זהה לתנאי ממש כאילו גם בתרגיל החדש הוא משהו על מינימום יש לו בסיסי
שמה זה?
לא, שנה שעברה לא היה כל כך הרבה,
היה אחד.
מינימום וזה
כן, כי זה...
שלושה תרגילים
כאילו, לא גמר.
סבבה, היא נכנסת שלי
אני חושב שזה טוב לחשוב פשוט על הקריטריוני האופטימליות השונים האלה, לא להידבק לאחד ולהבין גם שהם מדברים אחד עם השני. מיצית את אומרת.
לא, בסדר, אני לא מתלוננת. יש הרבה דברים להתלונן, אני מתלוננת. אמרת שתף, אני גל. גל בכלכלה כפית. מה? הוא לא באת בלוני גל. הוא אומר לי, טוב, הזמנתי, אבל תביא, לא, אתה...
Yeah, 20 shekels per month. That is good. Okay. See, you can't do it in your own home because it's really analogy to digital, and it's annoying to do that.
All right. So our key point at the end of last hour was that if you're non-Bayesian, you have to basically think of what your estimator does for every value of theta. You get a function that is sort of the performance of your estimator across different values of theta. And then I think it's easy to convince ourselves that it's hard to have an estimator that will always be better than the other. Why? Because these silly estimators are impossible to beat. Okay? If you always say 3, you'll get it exactly right one time, and you can easily convince yourself that no one else can do that. Okay? So you can't be perfect for 3 unless you always say 3. More or less. Okay? We'll be more precise about it later. But okay, so it just says that when thinking about optimality of these classifiers, we need to somehow think of comparing these curves, and this is something. Okay. So we'll do that later on in class, but first I want to discuss a simpler case where we have multiple ID observations, or we have ID observations, and we have many of them. Okay. So I want to consider a case where our observations are very informative or very good. And what happens in this case? So what would you expect would happen? If there's an unknown parameter and you see not x, but you see xn, and n goes to infinity.
So the hope would be that the estimator converges to the true value.
Exactly. Right? So this is something that's not unreasonable to do. Right? That if we have IID observations and we have an infinite number of those, our estimator will give us the correct value. Why? Because we're getting an infinite amount of information. So, it's okay to expect that it will be perfect. So what does it mean in terms of this performance curve? So as n goes to infinity, we'd like performance to be what? So if this is theta, and this would be our log.
Should approach flat 0.
Right, exactly. So we'd want it to be like a deadlock, okay? Which would be good. So it's uniformly excellent across all parameters, right? When did we see an example of this? Of something that behaves perfectly as n goes to infinity? When we talked about decision making with 2 states, right? Okay? There I convinced you, I hope, that as n goes to infinity, you're going to make the right choice always. Okay? Except in one case where the distributions are the same. Okay? It's impossible to make this decision. Okay. So this phenomenon is often known as consistency of estimators. Okay? So consistency, we will say that an estimator is consistent if it has this property that as n goes to infinity, it basically performs flawlessly, or is perfect. Okay? So let's just make that a bit more formal. So given, so
p from so let's assume x is discrete now, p of x given theta. Just because I don't want to write it because I'll do something. Okay. So given an estimator theta hat of x n, that's our estimator, we will say that theta hat is consistent if when we generate xn from p of x given theta for some theta, it's true that this thing, theta hat xn, so what is this thing? What sort of beast is it? It's a random variable, okay? So xn is drawn randomly from this thing. So this thing is a random variable, right? It's an estimate. So it's every time you see a different observation, there's a different outcome, right? Different estimate. Okay? So we want to say that as n goes to infinity, this converges to what? Well, this thing. And what is this thing? It's a number, okay? So it's convergence in what? So it converges in probability. Okay? So there are different notions of convergence, but we'll stick to this one. So convergence in the sense of the law of large numbers. Sorry? That's a different. There are different notions of convergence.
What do you mean when you say probability?
That the probability that that this will deviate from this by more than epsilon is arbitrarily low. Okay. Yeah. So I'll ask Roy again to cover the different notions of probability, of convergence and probability. Okay. But basically it says that if you have a large enough sample and you look at your estimator, it will almost surely have this value, or it will be arbitrarily close to it. Okay? Basically it'll get the answer right. Okay? Right. So let's see that this is not such a ridiculous thing to want. So let's take the example we had before of a Gaussian with unknown mean. So in this case, we saw that the ML estimator is this thing, right? That's what we saw last time, an hour ago. Okay, so let's ask ourselves: is this thing consistent? What do we need to do? We need to consider what happens if this goes to if m goes to infinity. Okay. All right. So actually, in this case, it's very easy to analyze. Okay, let me do it this way. So, what's the expected value of? No, let's do it more carefully. What is this thing? It's a random variable, right? Okay. What sort of random variable is it? It's a sum of n variables. Okay. What are these variables? IID what? Gaussians, right? What is the sum of independent Gaussians? Sorry? If they're independent. And they are. Okay? So the sum of independent independent Gaussians is a Gaussian, okay? And with what mean?
Some means.
The sum of the means, right? Okay? So let's say the expected value of theta hat mn, that's true anyway, even if it's not Gaussian, is just 1 over n, sum over I, expected value of xi. This is all for a particular value of theta. What's the expected value of xi?
Yeah.
Theta, right? So we have n times theta over n, so that's just theta, okay? So the expected value of our estimator is good, right? It is the correct case.
Don't you need to change the summation, the sigma notation with the expectation
Here?
from the above?
Here?
Yeah, from there to
here?
Yeah.
No, I just use linearity of expectation. So I did expectation of this is expectation of 1 over n this, and then I just took the constant out, and okay? And in the same way, the variance of theta hat ml xn, this is also generally true. What is it? It's the sum of independent variables, so the variance of the sum is the sum of the variances. What happens to 1 over n? Right. So this is 1 over n squared, sum over I, variance of xi, which we assumed is 1, right? So this is 1 over n squared times n, which is 1 over n. Okay? Right? Okay. So what happens to this variable? This variable theta hat xn. So this is value of theta hat, and this is f of theta hat xn. What does it look like? It's a Gaussian, right? Whose mean is what?
Yeah.
Theta. So this is theta here. And what is the width of this thing?
1 over square.
1 over n. Yeah, 1 over. Well, the variance is 1 over. Okay. Okay. So, do you understand the deviation or the variance? Okay, the width is the standard deviation. Let's say so it's 1 over square. Doesn't really matter. What matters is what? What happens as n goes to infinity?
It's small.
Right? So it basically narrows itself down until it's exactly what? Theta, right? So as n goes to infinity, this would be tightly fit at theta, which means it converges to that value. Okay? Right? So your estimator is a random variable. It has, for any finite n, it has some distribution. Okay, it's not always going to have the same value, but as n goes to infinity, it'll just converge and nail down the correct value. Okay, so two good things we learned from this. One is that the notion of consistency is not that unreasonable to ask for. Here's a simple estimator that is consistent. And the other good thing is that it's actually our friend DML, the maximum likelihood estimate. Okay? So, what is actually true, and that is perhaps more surprising, is that the ML estimator, under fairly reasonable conditions, is generally consistent. So this is not a random example. So maximum likelihood is generally consistent, whatever family you have. Okay? So it's not generally true, because you could come up with pathological cases where the family, the parametric family, is such that maximum likelihood is not consistent, but under what is commonly called in the literature regularity conditions. Oh, I didn't say so much. It is true. Okay? So when you look at the papers or textbooks on mathematical statistics, usually results are stated under certain regularity assumptions. That's the common terminology. And it usually means that things are nicely behaved, continuous, differentiable, etc. Okay, so there are no mathematical pathologies. So there's a theorem that says that the AML estimator is consistent, but that's not always true. It's under regularity assumptions or conditions on the parametric family. P of x given theta, or say P or F of x given theta, depending on whether your variable is discrete or continuous. Okay? Yep.
In the example you just gave there,
Mm-hmm.
so we assumed variance 1. But the question is, if we assume that the variance can we generalize that and assume that the variance is any parameter, and
Yep.
then we'll have A over, let's say the variance is A,
Mm-hmm.
we'll have A over square root n, and it's the same thing.
Do you want to assume that it's fixed or that it's unknown? Do you want to assume that it's always 3
There is a
or?
parameter.
Okay,
Then
yeah.
It doesn't have to be 1.
It will be the same, because what happens? They will both theta 1, theta 2. This is the example that I mentioned an hour ago, at the end of last class. That there is theta 1 and theta 2, unknown mean and variance. So there is the ML estimate for both. And what will happen is, as n goes to infinity, they will both the mean and the variance will hit the right value. Okay? Because the mean actually, if you think about it, the mean is exactly estimated in the same way, right?
Yeah.
It's the same estimator, so it has to be consistent. But the variance will also be consistent.
The only difference is that the standard deviation will be the parameter of the square root of n. That's what will come out.
Yeah, it will be the true variance, okay, over square root of n. Okay, but it's still, this is what the theorem tells you essentially, that this is generally true, not just for that particular example. Okay, so basically the good news here is that this ML estimator is for most cases of interest is consistent. So it's good in the sense that if you give it enough parameters, it'll nail down the correct parameter. Okay? Yep. So as I said, it's general conditions like differentiability, continuity, existence of second derivative, stuff like that. Okay. Sorry. That this function, yeah, either density or distribution is well behaved, so it's not too crazy with respect to either theta or x. Okay. Yeah, which most of I guess all of the examples you'll see are of that nature. Okay. All right. So I guess the theorem goes back to Fisher, and it was proven in various degrees of generality afterwards. So to actually prove it completely formally is a bit tedious. So I will do a semi-proof. I'll try to show you where I'm cheating. So let's call it an approximate proof. Okay, we can point you to the complete proof on the website. So what are we interested in is the limit as n goes to infinity of this thing here. Okay, so this is a random variable. Okay, so we're asking what does this random variable converge to? Okay, so it doesn't have to converge to a scalar necessarily. It doesn't have to converge to anything at all. It might converge to a distribution. Okay, to a random variable with a particular distribution. In our case, we'll show that it converges to a number. Okay, so it's the I'm sorry, I forgot to mention one key thing under these regularity assumptions. And so remember when we started talking about parameter estimations, I said that the setting could allow silly cases where you have two different parameters that specify the same distribution. Do you remember? What did we call that? Identifiability, right? So naturally, if a given distribution has two names, then it's we can't hope to get the right name, right? If one of you has two names, then and I call you one name and say, why didn't you call me the other one? Okay? You know the story about the Polish mother that buys two white shirts and so the child wears one. She says, well, you don't like the other. So anyway, identifiability. So we need identifiability in the sense that there is only one name or one parameter per distribution. Identifiability. Good. All right. So let's just write the definition of argmax over theta prime, let's call it. So instead of the likelihood, I'll do 1 over log P of x1 given theta. All right? So the argmax, all of this thing is the argmax. So here's one potential complication is that this there could be multiple maxima. Let's ignore that. Okay? I'll just mention things that one should have actually taken care of, but we won't. So when I write argmax, that implies I'll take one of them. Let's just assume there's one. Why did I do 1 over n and log here for the likelihood? Because when you take n to infinity, it's best that the thing that you're looking at will not go to infinity itself. Okay? That and therefore, if you take 1 over n, this is sort of the average likelihood, and this will not go to infinity. Okay? Yep. Because here. Oh, sorry. Is that what you want? Yeah. Sorry. Okay. Very good. So this is still a random variable here. Okay. So all this thing is this random variable, which is this complex function of this random variable. Okay. So here comes cheat number 1. I'm going to take the limit inside the max. Okay, I'm going to switch max and limit, which you really need to justify, but I'm going to do it anyway. Okay.
From regularity,
right, exactly. So it's something like that, but you need to really. Okay, but you could say it, but so switch lim and max. It needs to be justified. Sorry? In the test, you won't need to justify it. Okay. I won't expect more of you than I expect of myself. Right. So I will do that. You can go back to our proof of the consistency. I mean, for the two world state case, and see why it wasn't an issue there. Basically, because we had a max over just two things. But anyway, let's do that for just so we see what's happening. So I'm going to take the argmax, and then I'll do the limit inside. And then, okay, and then I'll do something else. I'll use the IID assumption. So this is 1 over n, sum over I. There's a typo in the notes. Please correct the typos in the notes if you observe anything. I mean, let us know. Okay. Right. So I just use the IID assumption. Okay. Okay. And now this sort of suggests what will happen now. So this, let's keep the argmax over theta prime. What is this thing? All of this. Yeah, it's the log likelihood, right? But it's also an average of n things that are what? Sorry? Random variables, right? So let's call all of this thing Zi, right? We've done this before. This should be a deja vu for you. So Zi are IID random variables, right? We're taking their average, okay? What does the average of IID random variables converge to? Right, their expected value. So, okay. So, and in other words, we've done this before, so I'll just jump to the conclusion. So this converges to expected value of z, given, of course, what? Where are these z's generated from? Yeah, but where are they? Who generates? What is the parameter that generates them? Theta, right? So there's a different theta. Okay, these x's, and therefore the z's, are generated by something, right? The true parameter. Okay? This theta prime is not a real parameter. It's just something that I'm maximizing over, right? But these, so there is still in the world this true theta, and this is what generates x1 to xn, correct? So the distribution of the x's is determined by what? By theta, right? Okay? And also the distribution of the z's, obviously. Okay? So this converges to the expected value of z's given theta, which is always in the background. This is the theta that generates everything. Okay? And this converges, again, in probability. Okay? According to what? Why is this true? What's the theorem? Right. By the law of large numbers. Okay. So what is this expected value of z? We'll use this the law of the unconscious statistician. So we'll average over x instead. So we're averaging over x, and it'll be p of x given theta log p of x given what? What is z? P of x given theta prime, right? Okay? So z here is defined. You set theta prime here, okay? And z is calculated for this particular theta prime. Sorry?
The other one should also be theta prime, right?
Should be what?
The first one?
This one?
Yeah,
No. No, they're different. There are two things happening here. The x's are generated from theta, okay? Z doesn't know anything about theta. Z is just defined as this thing, okay? Right? It's a function. It looks at x. It has this theta prime that was determined here, right? And it calculates this thing, okay? And that's where you get theta prime here as well, okay? It's a bit tricky. There are two things going on here. There is the data generating mechanism, which generates the x's, and therefore you need to take the expected value with respect to that, okay? So x's are, the probability is given theta, this true theta here, okay? And z just says basically this x, how likely is it given theta prime, okay? Z is testing different theta primes, right? Okay? So we're maximizing, outside we're maximizing over theta prime, and z here asks, it sees these x's and it asks what's your probability given theta prime, okay? Right.
So,
yep.
so how, I'm sorry if you just said that.
No, go ahead.
How did we perform, why is that expectation of what you wrote there on the right?
So you want you want the expected value of z, okay, given this value of theta, okay, given that everything is generated by theta, right? Mm-hmm. So in principle, this is sum over values of z, p z given theta. That's it, right? But now we have this law of the unconscious statistician, which says since z is a function of x, okay, so we can write it as sum over x, this function g of x, p of x given theta, right? And what is this g of x? It's what's written here. It's log of p of x given theta prime. All right? Okay. Good. So, all right. What happens now? Let's look at this thing. First of all, no more random variables, right? This this is a number. Okay? So we've done away with the random variables. All right. So this is a number. For every value of theta prime, there's a number here, right? Okay? So all this thing in here is a function of theta prime. Okay? Good. Now look at this thing. Does it remind you of anything? Sorry? It is like a DKL. If you see distribution, log distribution, okay, think DKL or entropy, okay? If it's P, no, it's a different distribution, okay? Because theta and theta prime are different, okay? So it's two different distributions. So it's P log Q. P log Q is very similar to a DKL, right? So sum over X, P of X log P of X over QX is exactly the DKL, right? Between P and Q. But here we have something a little different. Okay, we have P log Q, right? So let's think of what is P log Q. Let's write it here. So sum over X, Px log Qx is like minus sum over Px log Px over Qx. So this gives me the Px log Qx, right? And what am I missing? Oh, there's the P of X log P of X, right? So I need to add that back in. So this is sum plus sum over X Px log Px. Correct? So this is just equality here, right? Okay? So this here is the minus DKL between P and Q. And this thing here, I will denote it by minus H of P. Anyway, it is, you know what it is? This is? The entropy, right? I guess, have you all seen entropy? All right, doesn't matter. For those of you who haven't, this thing is some function of the distribution P, right? So let's just call it minus HP, all right? Okay? All right, good. So now I'm going to use this little insight that I collected there to write argmax over theta prime. So this is my P log Q, right? So it's going to be minus DKL between P x given theta and P of x given theta prime plus, or is it minus, the entropy of whom? P, right? Who's P? P of x given theta. Okay, so here's a nice thing. Look at that. Look at this. Should I care about this element here? No, because it doesn't depend on theta, right? It's an additive constant. So I'm going to. That's why I didn't really care if you knew entropy or not, because it's going to go away. No. So it's the argmax of minus DKL between P of x given theta and P of x given theta prime. Okay, and last bit, minus DKL, that's ugly. So I want to turn that into a minimum. What do I do? I mean, I want to get rid of, okay, I gave you the answer, it doesn't matter. So it's just the argmin over theta prime of the DKL, right? If you're maximizing something or minimizing its the negative, it's the same thing.
Why would you ignore the second term?
Because I am maximizing over theta prime, and this is just theta. There's a single theta somewhere in the world. Someone has chosen it for you. Okay, and you're not maximizing over it. Okay.
But anyway, we see that it depends on the property of the real theta, right? The solution we can achieve.
No, because the maximizer here, okay, whatever theta is, it doesn't matter because it won't affect the maximizer. Yeah. Okay. Theta does show up here. Okay. So, okay. Yeah, no, so that was wrong. Obviously, it will affect the maximizer, but this term will not affect it. Okay, good. So look at this thing. What do we have here? It's always positive, that's true. and we're minimizing over theta prime, okay? So what is the lowest value that this can get? 0. When will it get 0? When these two distributions are the same, right? When are they the same? When theta prime equals theta, obviously they're the same then. And according to our identifiability assumption, that's the only case, okay? So this leads us to the conclusion that this argmin over theta prime is exactly theta, okay? Because theta prime equals theta gives DKL 0 and identifiability. Okay? So basically, if we look at this thing, the theta prime that minimizes it is theta prime equals theta, and that's the only one that minimizes it because of our assumption. Okay? Good. So I only cheated a little bit. Okay? Well, actually, many cases, but definitely here when I switch the lim and the max. Okay? Actually, mostly. Okay? Yeah, and I assume x is discrete, which is in this case it's really 0 if and only if. If x is continuous, then there could be cases where two distributions have a DKL of 0, but they are not identical except for a finite countable number of places.
Why do you have to put the 1 over n?
Because then I can use the law of large numbers. This is important, okay? Because then this thing turns into an average, okay? Yes?
So just one question about the identifiability.
Mm-hmm.
What did you say about that? That we can know that this is the only case due to the identifiability, but
So if you had two parameters that correspond to the same distribution, okay, then they would both attain 0 here, right? If theta, you come up with the theta that's the real theta, okay? But it has two names, okay? And now I do the estimation. So obviously the min theta prime here could be one of the two, right?
so it means that the solution is unique.
Yeah.
The same like saying that the solution
It
is unique.
it means that the solution to this is unique. That there is a single parameter setting such that this is 0. Okay. So for the distribution P of x given theta, there is no other parameter that gives you the same distribution or that gives you 0 DKL.
Okay, and another question about
Yeah.
the 1 over n.
Mm-hmm.
The fact you were able to insert that into the equation is due to the fact that it's a constant. If you're looking for
Exactly.
so we are always able to do that when we're trying to find maximum or minimum. To
Mm-hmm.
multiply by
Multiplicative constant is fine.
it helps.
Okay. And log. So there are two things here, right? I took the log of the likelihood and then multiplied by 1 over n. It's something that we've done, I guess, a couple of times by now. Okay, good. So maximum likelihood is nice in the sense of consistency. And since this also tells you something about map, if we go back to the Bayesian case, what can we say about the map estimator? It's also consistent, right? Because we saw that it's identical to the maximum likelihood up to adding the prior. And we said that the prior is washed away anyway when you have infinite data, right? Okay? So if as n goes to infinity, Bayesian map is the same as maximum likelihood, then it's also consistent, right? So good. So it's reassuring for the Bayesians. Okay, so that's one nice property of an estimator. Some would argue that if your estimator doesn't have this property, then probably not much good. But that's, I wouldn't say that's an absolute statement. But you would think that you want something that as you get perfect information, it becomes perfect. But it's not. I mean, there are cases you could think of estimators that are not unreasonable that are also not consistent. Okay, so that's one property. And now, so I'll mention another property now, and we'll do something else in next class. So we have this estimator theta hat xn. As we said, That's a random variable, right? So in some cases, I mean, if you fix theta and you generate different distributions, you're going to get different outcomes for this theta hat, right? Okay? So a simple thing that you might want this thing to satisfy is that, okay, let me say it a different way. Let's say the true parameter is 3, okay? And now you, okay, so 3 theta equals 3, and now you generate one xn, a different xn, etc. And for each of those, you do the estimation, okay? Let's say these are Gaussians with mean 3, okay? So if you take the average of your sample, maybe sometimes it's going to be 3.7, 2.5, I don't know, 4.6, etc. Okay? It's a random variable, right? Every time you draw a different sample, you get a different estimate. Okay? So it might make sense to ask that these numbers, even if they don't hit 3 exactly, on average, they're 3. Okay? It's like in the casino. You say sometimes you're up, sometimes you're down, but the horse always wins. Okay? I guess it's not exactly the same, but anyway, you might think that it's a reasonable thing to require from an estimate, that in expectation, it has a true value. Okay? So it's not like saying it doesn't have any spread. We're just saying, in expectation, I want it to be to give it the correct parameter.
But what is the difference between this and to say that when n is going to infinity, it's going to be 3?
Well, because that's more restrictive. If you ask, as we did before, that as n goes to infinity, you get the right value, it only applies when you have an infinite number of samples.
But when n is very big. So you're saying if we have 3 situations, 10 observations for each, so the average should be 10. But what's
Right.
the difference between that and having 30 observations?
Well, because sometimes you just have 10. Let me define the property and we'll see, okay, what the difference is. Okay, so let's say unbiased estimator. That's the property we're interested in. And then the definition is we will say an estimator is unbiased if when sampling xn from p of x given theta, it holds that the expected value of theta hat xn equals what? Theta. All right. So just to make things clear here, we'll say the expected value if you draw x from theta. Okay.
So we say that for every.
Right, for all. If sampling from it holds from if, okay, so if for all theta should be here, okay? So regardless of the theta that you choose, okay, if you play the game of repeatedly generating samples and take the average of your estimator across samples, or the expected value, you get the true thing, okay?
For all n.
Let's say this for a particular n, okay? You could have an estimator that only works for n equals 5, right? Okay, so, right, and this is for finite n, okay? So back to your question, so we're talking about the case here where n might be 1 or 2, okay? So it doesn't go to infinity, okay? So in this case, I'm not saying that you get always the exact value. This is just an expectation, all right? So you will very often be wrong, like here, okay? So here is sometimes 2.5, which is away from 3, or sometimes 3.7, which is always also away from 3. But on average, the average is 3, okay?
The thing that is still not clear is, okay, but I can ask later.
Oh, go ahead.